It is known that only 3% of the water on the earth is fresh water, which can be used in daily life. Water is essential to humans as they need it to survive, but not all humans currently have access to clean water. Therefore, both engineers and non-engineers must work together to provide the world with the clean water needed to survive. It turns out, in order to access more clean water, desalination would be one of the most effective methods to address the problem. However, desalination would usually be expensive and energy-consuming. Such drawbacks would not be friendly nor appropriate for developing countries. One of the potential solutions for this problem is nano-desalination. The introduction of such technology would not only greatly improve the recycling of contaminated or wastewater, but also directly reduce the energy use. The nanostructure of graphene would provide enough drag force to suck the water molecules from salty water, as mentioned by RSC advances. At plunger speeds of 0.5 cm per second, the desalination occurs via a quasi-equilibrium process, which minimizes the energy necessary to drive desalination. Material engineers need to fully appreciate the different compositions between filtration devices for circulating water types, such as the molarity concentration of carbon in desalinating filters. They also need to track the performance on each filter to check whether they are qualified. In this case, that would be the rate of molecular separation and plunger speed. In addition, materials engineers can work in conjunction with chemical engineers to design filters, and other process needed for wastewater treatment is another way to get clean water. As stated in an article in Chemical Engineering News, expertise is needed to develop technologies and design multi-step processes required to treat industry chemically complex wastewater streams. Wastewater can come from a variety of different sources, such as domestic sources, commercial sources, agricultural sources, rainwater, and runoff water. The water goes through a primary treatment, which includes screening, comminution, grit removal, and sedimentation. The water then goes through a secondary treatment, which removes the matter that is left after the primary treatment. This removal is done by microbes consuming the organic impurities as food, converting them into carbon dioxide, water, and energy for their own growth and reproduction. In order to improve the efficiency of obtaining purified water, the regional government needs to figure out where the purified water should go. For example, there are at least two types of filtered water: recycled domestic water for daily use and recycled industrial or irrigation water. Such divisions would need assistance from non-engineering fields, which are the regional health bureaus and farming or agricultural units. Different branches should be aware of their water demand and submit a detailed report to engineers, like for irrigation and agricultural water, which should be less restricted than household water. The regional governmental institutions have to designate who has a priority to the water based on their community's needs. They have to distribute the water that was purified through engineering technology in a way that satisfies the United Nations' Sixth Sustainable Development Goal, which is to ensure availability and sustainable management of water and sanitation for all. In conclusion, access to clean water is a worldwide issue, with billions of people suffering from the lack of proper water and sanitation. Chemical and material engineers should work collaboratively with regional governments to provide clean water to people in impoverished areas. There have been many strides in the development of clean water technology, like nanofiltration that allow contaminated water to be consumed safely. Hopefully, many of these people will be able to gain access to clean water with the help of these engineers and new technologies.